Hello, everyone, and welcome to this training session on methodology for riser interference analysis in Orcaflex. My name is Mehdi. I've worked across naval architecture and subsea SURF engineering and checking whether dynamic flexible systems interfere with each other has been a key part of my role. In this video, I will explain the purpose of interference analysis, the key load case inputs, and the practical methodology used to assess whether a riser or subsea line configuration is acceptable with respect to clearance and clashing. The main objective of this training is to explain how interference analysis fits into overall subsea design process and how it is used to support safe and optimized configuration development before the later structural assessment are performed. With this introduction, let's begin. This is the agenda for the training. First, I will explain what interference analysis is and why it is important in subsea design. Then, I will discuss the main drivers of interference between two subsea lines. After that, I will review the interference acceptance criteria. In the second part of the presentation, I will explain the overall interference analysis methodology, how to the load case matrix is defined, and how the load case matrix how the load cases are generated automatically in Orcaflex. So the presentation moves from basic concepts to practical workflow and implementation. This introduction section answers four basic questions. First, what does interference analysis mean in Orcaflex? Second, why is it needed in subsea design? Third, what are the main sources of interference between two subsea lines? And finally, what acceptance criteria are used to judge whether the configuration is acceptable? These 4 points form the foundation of the methodology to be presented later in the training. What is interference analysis in Orcaflex? In Orcaflex, interference analysis is the assessment of whether two nearby subsea lines lose clearance or come into contact during the simulation. In practical terms, it is used to check the relative movement of the two lines and to identify any risk of clearance loss, physical contact, or clash. Orcaflex supports this using line clearance results, line clashing, and line contact capabilities. Because of that, interference analysis helps engineers make decisions on spacing, routing, configuration, and overall integrity risk. So, the key message on this slide is that interference analysis is not only a geometry check, it is a relative motion assessment of clearance loss, contact, and clash risk. Why it is needed in subsea design? Interference analysis is needed in subsea design for several reasons. First, it is used to confirm minimum clearance between nearby subsea lines in all relevant cases. Second, it helps identify contact or clash risk that could affect line integrity or operability. It is also an important tool for configuration design and optimization. In other words, it helps us confirm whether the selected routing, spacing, kickoff arrangement, azimuth, dynamic length, buoyancy layout, and auxiliary subsea components are acceptable with respect to interference. If the interference criteria are not met, the subsea configuration must be updated. For example, we may need to revise the route, kickoff angle, azimuth, total dynamic length, buoyancy module definition, or the use of tether or holdback devices. This is why interference analysis is usually performed before the later structural assessments. First, we confirm that the configuration is acceptable with respect to clashing. Then, the accepted configuration can proceed to strength, extreme, fatigue, and global in-place assessment. The main drivers of interference between two subsea lines are shown here. These include insufficient initial spacing or routing separation, different static or dynamic line shapes, current-induced excursion, wave-induced motion, vessel offset or imposed end motion, buoyancy section interactions, touchdown point migration, and installation or transient conditions. The important idea is that interference is mainly driven by relative movement between two lines, not only by the nominal layout. So, even if the initial routing looks acceptable, the combination of environment, geometry, and dynamic response can still bring the lines too close together during the simulation. Interference acceptance criteria are project specific. In many projects, the interference methodology reference is DNV RPF 203. A common minimum spacing rule can be written as minimum clearance greater than or equal to D1 plus D2 plus marine growth thickness if marine growth is applicable. Here, D1 and D2 are the diameters of the two subsea lines. Other projects may accept smaller clearances if no physical contact occurs. In some cases, limited low severity contact may be acceptable, but only if it is explicitly allowed by the project basis. The key point is that if the acceptance criteria are not met, the subsea configuration must be revised and reassessed before the design can move forward. This slide marks the transition to the methodology section. In the next part of the presentation, I will first explain how the interference load case matrix is defined. Then I will explain how the interference load cases are generated. So from this point onward, the focus moves from the basic concepts to practical workflow used in the analysis. The interference load case matrix should include all the variables that can significantly affect relative movement, clearance, and clashing risk. This typically includes the governing environment, any special current or environmental profiles, the primary and associated environment directions, wave data if relevant, vessel offset magnitude and direction, marine growth condition, and any sensitivity cases when the result is close to the acceptance limit. The purpose of the matrix is to make sure that the governing interference scenario is not missed. In other words, we want to cover the cases that can realistically bring the two lines closest together. In the previous slide, we defined the load case matrix. Now, the next step is to translate that matrix into actual Orcaflex models. To do this, we need a clear set of input parameters that can be varied automatically for each interference load case. These are what I call the primary parameters for automated interference load case generation. They include the base or Koflex model file, wave parameters, current parameters, vessel offset parameters, line drag coefficients, and wake interference parameters. The concept is simple. The base model contains the fixed project configuration and data, and the automated workflow varies only load case dependent parameters required for the interference study. In the following slides, we will look at each of these parameters groups in more details. The base OrcaFlex model file should be the fully validated project reference model. It should contain all data that are common to the full load case matrix. This means the base model acts as the parent model for automated variation case generation. Typical case variation inputs include seabed and water depth definition, line structural properties and geometry, fixed layout and boundary condition data, permanent attachment such as bend stiffener, bend restrictors, buoyancy, clamps, holdbacks, and invariant vessel or hydrodynamic data such as vessel type, vessel type properties, and RAOs. Then the Excel spreadsheet and text workflow change only the load case dependent parameters such as waves, currents, and offsets, as well as other study specific variations. For wave parameters, the exact input depends on selected wave formulation. For regular waves, the main inputs are direction, height, period, and selected wave theory. For irregular waves, the main inputs are direction, significant wave height, peak period or zero crossing period, spectrum type, and gamma where applicable. In some studies, time history waves are used. This means a direct wave elevation record is applied when a measured or externally generated sea state history must be reproduced. Another option is user specified components. In that case, the wave train is defined as an explicit set of sinusoidal wave components, which is useful when full control of wave train is required or when matching another tool. Additional inputs such as wave origin, directional spreading, random seed, and spectrum discretization may also be required. In this workflow, the current inputs used in the Excel spreadsheet are simple. Usually, we define the current by three items: current name, current direction, and current speed. The current name selects the predefined current profile case. The current direction defines the flow direction, and the current speed defines the reference current magnitude. This works well when the detailed current profile definition is already built into the base OrcaFlex model. This slide explains the logic of vessel offset definition. The vessel offset is generated using a five-stage prescribed motion sequence. Typically, the vessel is held, accelerated, moved at constant speed, decelerated, and then held again. The offset is the distance traveled during this motion program. So the area below the velocity time graph is equal to the vessel offset. The key practical point is that the duration of the constant speed stage is adjusted to achieve the required offset. These durations are not fixed rules, they are practical values chosen to reduce transients, create create a controlled offset maneuver, and provide enough time to assess the interference condition once the target offset is reached. This slide shows the same vessel offset logic in the Orcaflex table format. Each row represents one stage of prescribed motion with its duration, time range, speed mode, speed value, direction of motion, and rate of turn. Stage 0 is the initial hold. Stage 1 accelerates the vessel. Stage 2 moves the vessel at constant speed and creates most of the offset. Stage 3 slows the vessel down, and stage 4 keeps the vessel at the target offset. The time used here are practical engineering values. The 15-second hold at the start helps the model settle before the movement begins. The 15-second ramp up and ramp down stages avoid unrealistic speed jumps and reduce transients. The constant speed stage is calculated from the required vessel offset, and the 800-second final hold gives enough time to assess clearance and clashing at the target position. The motion direction is defined relative to global x, but the actual angle is updated for each load case using the wave direction from the load case matrix. So the directional changes from case to case in line with the environmental heading being analyzed. And the red entries in the table are the case dependent values. They must be updated for every interference load case so that the vessel motion matches the required offset and the correct environmental direction. This slide explains why line drag coefficients are important in automated interference load case generation. In Orcaflex, the base drag coefficients are defined in the line type data. These coefficients are used to calculate the hydrodynamic drag force acting on the line. Orcaflex defines drag coefficients in the normal and axial directions, and the normal drag coefficients can be constant or can vary with parameters such as Reynolds number, and height above seabed. For interference analysis, the starting point is always the project base drag coefficients. But in some cases, this is not enough. If the project design basis requires it, we also include VIV drag amplification. In that case, the effective or inclusive drag coefficients is calculated as the base drag coefficient multiplied by drag amplification factor or DAF. This is important because when vortex induced vibration is possible, the effective drag on the line can be higher than the basic hydrodynamic value. Orcaflex itself notes that if significant VIV is expected, the drag coefficients may need to be increased. Another important point is that the DAF is not always constant along the full line length. It can vary with line section depending on the response of the line and the project's hydrodynamic basis. So, in practice, the inclusive drag coefficient may be different in different parts of the same line. Orcaflex supports this because its fluid load setting can be applied on a section specific basis. Also, If the project basis defines different drag of DAF distributions for different lines, then those differences must be respected in the generated interference cases. In other words, each line may require its own inclusive drag definition, and that definition may also vary along the line lengths, and Orcaflex line section and line types allow this level of definition. So the key message from this slide is that drag coefficients are not just default hydrodynamic inputs. In interference analysis, they are part of the case definition and may need to be adjusted to reflect VIV amplification and section by section behavior. Wake interference parameters are defined section by section in Orcaflex. In an upstream and downstream interference case, the upstream line is assigned as the wake generating line, and the downstream line is assigned as the wake reacting line. So, for the upstream section, we select the required wake model, for example, Hughes, and for the downstream section, we enable reacting to the wake. The key point is that the wake is generated by the upstream line and modifies the hydrodynamic loading on the downstream line. At this point, I have completed the review of the primary parameters used for automated interference load case generation. In the next part, I will move on to the interference analysis methodology itself and explain how these generated cases are used in the engineering assessment. This slide summarizes the overall interference analysis methodology. First, define the relevant pairwise interactions. For example, umbilical to umbilical, umbilical to steel catenary riser, or umbilical to mooring line. Second, build a project fidelity based model containing all fixed configuration data. Third, generate the load case metrics from the governing ocean and operational basis. Then, assess whether the selected subsea configuration is acceptable with respect to clearance and clashing. This is important because the purpose of the interference analysis is to confirm that the configuration is safe and optimized before other structural checks are performed. If the interference criteria are not met, the configuration must be updated and the analysis must be repeated. Typical updates include subsea route, kickoff angle, azimuth angle, total dynamic length, buoyancy module dimension, location, number, or the use of tether or holdback devices. Only after interference acceptance is achieved should the configuration precede the strength, extreme, fatigue, and global in-place analysis. This slide highlights the role of interference analysis in configuration development. Interference analysis is used to confirm that the selected riser or subsea line configuration is acceptable and optimized with respect to clashing risk. If interference acceptance is not achieved, the configuration must be revised. Typical updates include subsea route, kickoff angle, azimuth angle, total dynamic length, buoyancy module size, location, and number, or the use of tether or holdback devices. So, interference analysis is not only a final verification step, It is a configuration qualification step that should be completed before strength, extreme, fatigue, and global in place assessment of the final accepted configuration. In this part of the training, I want to show how the Excel spreadsheet and the Orcaflex text template file work together to generate the interference load cases. This example is for training purposes only, and I've considered only two load cases, so the workflow is easy to follow. In, in a real project, the same approach can be extended to many more cases by adding more rows to the Excel spreadsheet. In this spreadsheet, each row represents one interference load case 1, load case 2. Each column represents one input parameters that may change from case to case. These parameters include the base model, the OrcaFlex base model, the stage duration, prescribed vessel motions, current direction, current speed, wave direction, and the drag related to different section of the subsea lines. In this training spreadsheet, it is assumed that line 1 and line 2 each have 5 sections, so the drag coefficient can be controlled section by section. Section 1 to section 5 related to line 1, and the same for line 2. And these are related to wake model and wake reaction to the subsea lines. For easy access, I copied the text file here to show. The text template file acts as the link between the Excel spreadsheet and the OrcaFlex base model. It starts from the base OrcaFlex model using the base file command and then updates only the parameters that change from one load case to another. In this example, in this example, the base model is referenced to the model placeholder, which is replaced by base model.dat from the Excel spreadsheet. The template also updates the general simulation stage duration. These stage durations are used for the prescribed vessel offset motion. The spreadsheet provides values for stage duration 1, stage duration 2, stage duration 3, and stage duration 4. The key variable here is usually stage duration 2 because it controls the constant speed part of the vessel motion, and therefore controls the target offset. Next, the template updates the environmental parameters. In this training example, the environment section includes the wave direction, reference current direction, and reference current speed. These values are taken directly from the spreadsheet for each load case. So, when the current direction or wave direction changes in the matrix, the generated OrcaFlex variation file is updated automatically. Then the template updates the line drag coefficients. In the template file, I define find line types for line 1 and 5 line types for line 2. Each line types has its own normal drag coefficient in x direction, and each coefficient is controlled by a spreadsheet placeholder. This is this is useful for interference analysis because drag amplification or section specific hydrodynamic behavior may vary along the line. After that, the template updates the line section definitions. For line 1, section 1 to 5 are assigned to corresponding line 1 section line types. Similarly, for line 2, section 1 to 5 are assigned to the corresponding line 2 section line types. In this way, the generated load case file connects each physical line section to the drag coefficient selected in the spreadsheet. The template also includes the wake interference settings. In this training example, line 2 is treated as the upstream line, and line 1 is treated as the downstream line. Therefore, line 2 is assigned the wake model, for example, the Hughes model, while line 1 is configured to react to the wake. These values are also controlled from the spreadsheet, so the wake setup can be changed from case to case if required. Finally, the template updates the FPU or vessel prescribed motion parameters. The speed values and direction values are taken from the spreadsheet and inserted into the FPU object in the text file. This is how the vessel offset motion is generated automatically for each interference load case. The base OrcaFlex model contains the fixed model data. For example, it contains the line configuration, the vessel object, the seabed definition, and all other data that don't change between the two load cases. The spreadsheet and the text file only update the load case dependent inputs. There are two practical modeling points that are important before running interference analysis. First, clash checking must be enabled for the line sections where contact may occur. In OrcaFlex, line clashing is only calculated when clash checking is active and the contact stiffness is non-zero for both potentially clashing sections. So if I want to check interference along the full suspended length, I need to active clash check for all relevant sections of both lines. The second point is related to buoyancy module modeling. If VIV analysis is performed before the interference analysis in order to obtain drag amplification factors, the buoyancy modules should be modeled discretely, not as a continuous or smeared buoyancy section. This is important because VIV response and resulting DAF or DAF distribution can be affected by the actual buoyancy module arrangement, including module location, spacing, diameter, mass, buoyancy, and drag properties. Although OrcaFlex allows buoyancy to be modeled either as discrete buoyant clamps or as smeared properties over a line section, the discrete approach is required in this workflow to represent the real local hydrodynamic and structural discontinuities used for VIV assessment. Therefore, if the VIV analysis is used to generate DAF values for the interference model, the buoyancy module section should be represented discretely in the interference model. For example, using clamp type buoyancy modules at the actual module locations. This keeps the line shapes, local hydrodynamic properties, and section specific depth application consistent between the VIV analysis and the interference analysis. To generate the load cases, I use the OrcaFlex Excel add-in. In Excel, I go to the OrcaFlex tab and run the create tab data file command. When this command is executed, OrcaFlex reads each row of the spreadsheet, finds the matching placeholders in the text template file, and replace each placeholder with the corresponding value from that row. As a result, OrcaFlex generates one complete variation data file for each load case. For example, the first row in the spreadsheet generates the first load case file, and the second row generates the second load case file. If the wave direction, current direction, vessel motion direction, drag coefficients, or wake settings are different between the two rows, those differences are automatically written into the generated OrcaFlix files. One important practical point is that the OrcaFlex base model file, the Excel spreadsheet, and the text template file should be located in the same folder. This is important because the template refers to the base model using a relative file path. If the file are in different folder, OrcaFlix may not find the base model or the template correctly during load case generation. After the file, After the files are generated, I should not run the full batch immediately without checking. First, I open one or two generated files and confirm that the placeholders have been replaced correctly. I normally check the wave direction, current speed, vessel prescribed motion values, stage duration, drag coefficients for each section, and wake settings. Only after this QA check should I run the simulations. So, in summary, the Excel spreadsheet defines what changes from one interference load case to another, and the text template define where those changes are applied in the OrcaFlix model. This is the basic workflow for automated interference load case generation. Thank you for your attention. I hope this training has given a clear understanding of why interference analysis is important, how the load cases are defined, and how the methodology is applied in OrcaFlex. The key message is that interference analysis is used to qualify and optimize the subsea configuration before the later structural assessments are performed. Thank you again for watching.